In this chapter, we will look at forces that slow us down, aerodynamic drag and bicycle velocity, static and dynamic pressure, bluff and streamline shapes, viscosity and Bernoulli's principle, and fairings.
Said a courier with a large bag, I will countenance any price tag. Please help me deduce how I can reduce my aerodynamic drag. The topic of aerodynamics is a very broad one, and we could spend a lot of time talking about the aerodynamics of the bicycle itself. We'll cover a little bit of that, but then we'll delve very deeply into the aerodynamics of wheels.
This is one obvious way to think about aerodynamics. Whether we are riding on level ground or in hills, there are four forces that slow us down: the force of air, rolling resistance, friction, and bumps. And we're going to specifically look at the power that's required to overcome these four forces. We're going to begin by looking at rolling resistance, friction resistance, and bump resistance. For these three, the power to overcome those forms of resistance increases with velocity raised to the first power. So it's a one-to-one relationship, which makes it linear. However, the power to overcome the force of air is proportional to velocity cubed, which makes it nonlinear and exponential. An example will make this clear. Let's say we want to increase our speed from 18 to 36 miles per hour, which is doubling. The power to overcome the force from rolling resistance, friction resistance, and bump resistance will increase by 2 to the first power. And that is 2. But the power required to overcome the force from the oncoming air will increase by 2 to the third power, which is 8. So if you want to learn how to ride fast, the only way to do that really is to reduce aerodynamic drag. That is the 800-pound gorilla in the room. Now, fluid dynamics is a field of engineering that looks at the properties of fluids and how they pass around and through objects. When we talk about fluids, liquids and gases are fluids. Air is a fluid, and air can be studied in wind tunnels. We study airplanes in high-speed wind tunnels and things like bicycles in a low-speed wind tunnel. Fluid dynamics explains a lot of things we see around us every day. One is an airplane's wings lift, a curveball, two ships sailing too close to each other, colliding, fast bicycles, tandems, and drafting. There are two kinds of pressure. There is static pressure, which is measurement of the ambient barometric pressure. At sea level, it is 1 atmosphere or all of these equivalent forms of measurement of pressure. The other type is dynamic pressure, which involves movement and the air pushing against a surface. I want to introduce you to David Gordon Wilson, who you see standing next to me. His book on the left, Bicycling Science, is a must-have, published by the MIT Press, and Dave and the MIT Press were kind enough to let me use some graphics that you'll see in some upcoming slides.
Now that we know that aerodynamics can be a big problem for cyclists, how can we go about reducing it?
There are effectively two ways to reduce aerodynamic drag. One of those is to reduce the frontal area of the rider and the bike. As the frontal area decreases, the force also decreases. This nice graphic here shows quite effectively a picture of the cross-sectional area of the rider and the bike. This is a friend of mine, Tom Bailey, and if we look from left to right, we can see 5 different positions representing different frontal areas. Here he is standing up. Here he is sitting down with his hands on the bars. sitting down with his hands on the brake hoods in the drops, and in this position here, a nice aero profile. So going from left to right, we obviously have a decrease in Tom's frontal area. The second way to reduce drag is to improve airflow around objects, and we see here there are two kinds of shapes. There are bluff objects and streamline objects, and we'll look at each of those. Bluff objects, such as we see here, are irregularly shaped. They have defined sharp corners, such as cubes and cylinders. On a typical bicycle that is not designed to reduce drag, just about everything you see is bluff. The rider, the round tubing, the round spokes, handlebars, helmet, shoes, loose clothing, and fenders. These are all bluff objects. Air has difficulty getting around bluff objects. We see in the graph here that there's no smooth flow. The air separates, and we find that we have behind the object a wake of unstable air with eddy currents, low pressure areas, partial vacuums. So bluff objects represent a large dynamic pressure drag from the onrushing air. Streamline objects, on the other hand, have no irregular shapes. The air passes more easily, less separation, fewer eddy currents, and less energy sapping wake. This is Daniel Bernoulli, lived in these dates. He was a Swiss mathematician and a major contributor to fluid dynamics. Viscosity is a measure of how easily a fluid flows. So, for example, molasses has a high viscosity, but water and air a relatively low viscosity. Now, here is Bernoulli's principle, which is this. For a low viscosity fluid, as the fluid speed or velocity increases, the sideward pressure decreases. The sideward pressure is often referred to as the normal pressure, or the perpendicular pressure, or the orthogonal pressure. Here are three nice graphics from Dave Wilson's book, and we're going to look at each of these. In this first image, we see air striking an object, and it begins to flow around the object. The second image is a continuation of the first if we have a streamlined shaped object, so that the air continues to follow the surface. The air remains attached, and we get a smooth, streamlined flow. Something else which is interesting happens in this case here. We actually, by looking at these little blue arrows here, we see that we have what's called return energy. And if we actually look inside a box, we can see what this means. This is a blow up of the blue line. That is the vertical component, and that is the horizontal component. So the horizontal component actually, which we see here, represents return energy or pressure recovery, and there is a forward pressure on the trailing edge of the aerodynamic surface in the form of that pressure recovery, or that little red arrow. But instead of an arrow shape, if I have something round like we see in the diagram at the bottom, then we find that the air detaches right here, and that creates in its wake partial vacuum and eddy currents, which we see here. So our round object, which could be a piece of tubing on the bicycle or it could be a round spoke, is trying to move forward, but it's always being pulled in the other direction by a backward drag. So just looking at these two cases in isolation, as they both move forward, in the case of the streamline object, we actually get a little bit of help pushing it forward, whereas in the other case, we have drag trying to pull it backwards. In this graphic here of a flat plate, we see as the wind hits it from the left, there's quite a lot of turbulence and drag in the wake of the flat plate. A cylinder is better. There's less turbulence. The third graphic is a cylinder with a trailing edge fairing, and before I explain that, let me show you what I mean by a fairing. This is a bicycle wheel that has a rim with a fairing. This whole part here is a fairing, and it is designed strictly to add an element of the aerodynamic drag reduction. It is not a structural component. That is where the actual inside part of the rim is, where the spokes attach, and that would be the bottom of the spoke bed. So you see here that a spoke actually disappears into the fairing and continues back here, and the nipple is way in the back and is accessed from the back of the rim. So you can see that the fairing here is not a structural member. But the fairing, even though it's not structural, is effective in reducing wake turbulence behind the rim. Now, not so much in wheels, but in other parts of the bike, particularly in elements of tubing, you'll see cylinders with a leading edge and a trailing edge fairing. So there's the leading edge and there's the trailing edge, and you see here a even further reduction of drag. This is another depiction of drag and pressure contours around the same four objects.